Externalities come in many different shapes and flavors and in different degrees of complexity and subtlety, and it's important to do that in order to have good intuition, to start with simple cases. So I'm gonna first spend a lot of time working on what we're gonna call public bats. It's a particular type of externality that has the following features. They are negative. In other words, they harm others. And they are non-targeted. And by that I mean that they tend to affect everybody in a side of the economy. For example, all consumers, or all firms, or everybody. Let me give you examples of public bats are CO2 emissions and global warming. If we end up experiencing global warming, and that's caused by emissions of CO2, every time you drive your car, you're hurting all other consumers and all other firms. Noise pollution, this is very common, for example, in Spanish cities. This tends to affect all consumers living in the neighborhood. And the fact that one person is affected doesn't decrease the ability or the extent to which others are affected. And another one is something that we actually saw before, which is poverty. If you have a situation in which people have social preferences, and for example, they feel bad from knowing that there are other people in their economy, in their country, that are poor, the fact that there are poor people, somebody not being able to reach a living wage and sufficient income will cause a negative externality, a public bat for everyone. Now we're going to start our study of the public bats with a very, very simple model that is going to allow us to develop in a very clear way some key results and intuitions. And then we will complicate it or look at different, more complex versions of the model in applications in the practice problems and in the problem set. So again, this model is very simple, but it's simple by design to really clarify some ideas. So we're going to look at a market with three goods. There's going to be the goods Q and M that we have always been looking at, and in addition, there's going to be this good E. And you can think of this as the externality, and if you want to keep a concrete example in your mind, for example, think of pollution, some sort of pollution. And another important thing is the technology of the externality. What is the production function of the externality? And the idea is that every time one unit of Q consumed, every time a consumer consumes a unit of Q, it generates 1 unit of E. Notice that this doesn't have to be integers. If they consume 0.1, it leads to 0.1 of E. Now we're going to assume that there are n identical consumers and that they have the following utility function, and now depends on Q, M, and E. It's like before, a benefit function of Q plus M minus gamma D of E. And this D of E has the property that is positive and potentially increasing at either constant rates or increasing rates. So in other words, if you have E, D will be like this or like this. Now a couple of comments. You can think of this as the damage as a function of E, which is the total level of the externality in the market. And you can think of gamma as a parameter greater or equal than 0 that tells you how big is the damage, how important it is. And we can turn on and off the level of the externality by turning on and off gamma. In this simple model, there are also going to be F identical firms. And these firms are going to have a constant returns to scale production function, so their C of Q is an identical mu of Q. So you have a lot of experience computing the equilibrium of markets in which look like this. They are competitive, but there is no externality. I'm going to add here as a reminder in your note that the market is competitive. Okay, now the only thing that has changed here is that now every time a unit of Q is consumed, it creates a unit of externality that affects everyone. Everyone, that is key. To be able to characterize the outcome of the market, we need to define a notion of market equilibrium. As you will see, the notion of market equilibrium is very similar to the one for a purely competitive equilibrium, and that shouldn't be totally surprising given that it's a competitive market. So in the market equilibrium, two things are going to be true. First, every consumer is utility maximizing, so there is utility maximization and profit maximization by all firms and consumers. Importantly, taking as given the total level of the externality. So the idea here is that there are many players in the market, all of whom affect the externality, and therefore when they are choosing their actions, they don't think that they can affect the total level of externality. Much in the same way, when you drive your car, you probably don't think by yourself you really are going to change during that decision global warming. And the second is that prices adjust so that market clears, just as before. So what does this mean in practice? Let's look at the problem of the consumer. The consumer is going to maximize how much to buy, so over Q greater than or equal than 0, how much to buy in the market. It gives him this much benefit, minus direct benefit, minus it has to pay this much. It also gets this externality that depends on E, but importantly, this is a constant since it's taken as given. And what does this imply? This implies that the demand function for the consumer and the demand function for the market is just as without externalities. Nothing has changed in this particular case. Notice that this is true in particular because the externality, if you're thinking carefully about this, is additively separable. There are cases in which the demand function can change, and we will see in examples later. But in this particular simple model, nothing has changed. What about the problem of the firm? Well, the firms, as before, are going to maximize over Q greater or equal than 0 their revenue minus their costs, which we have assumed as CRS. So we're going to have, again, the same supply function and the same supply function for the market, which is 0 if price is less than mu, anything if price is equal than mu, and infinity if price is greater than mu. So this is a market equilibrium that you have solved in homeworks many times and should be very obvious. Now that we know the market allocation, let's study whether or not it's efficient. And to do that, first we need to look what do optimal allocations look like in this simple market with public bats. So we know that an optimal allocation has to maximize total utility in society, the sum of the utilities, and we know from a lot of previous work that we can write this as maximizing over positive consumption of Q, the sum of the utilities for the individuals, where we can write like this, the sum of the BQI minus, and this is for every I, the damage from the externality, which is Q total, or the sum of the QIs. Remember, this is the externality, minus the cost of producing this level of QI, because that has to be discounted out of what they get to consume on M. And what you get, since the B functions and the D functions are identical, is that every one gets to consume at a point in which B prima Q total divided by N minus gamma N D prima at Q total is equal to mu. Everybody is a symmetric allocation because individuals are identical, characterized by this formula. So notice that we can write this formula like this, or we can pass it on to the other side. But basically, one important intuition here is that this is the marginal cost of producing Q. And that this is the marginal benefit. Let me be precise. This is the marginal social, I'm going to do it by MSB, the marginal social benefit of giving additional units of Q, an additional unit of Q to anyone. Okay, let's get some intuition for this. Suppose that gamma was 0. If gamma was 0, if this was not there, the marginal social benefit would just be the marginal benefit for that person, and the optimum has to be equal to the marginal cost of production. The problem here is that we have here the marginal externality. Every time you give a unit of Q to someone, you increase their marginal benefit of consumption by B prima of this, but you also create damage on everyone. How much damage? All of this much. And therefore, the marginal social benefit in this case is less than the marginal private benefit, which is just equal to the B prima of Q total divided by N. Notice that in this simple example, the marginal social cost is equal to this marginal cost of production. There is no externality on the production side, therefore the two things are the same. In this simple case, the optimal allocation has a very nice graphical representation. So again, the VQ, let be these dollars per unit. We have mu, which is equal to the marginal private cost, and is equal to this marginal social cost of producing Q. And then we have the inverse demand function for the market. And notice that this function can be written as B prima Q total divided by N. Why is that? Because we knew that this was the aggregate marginal benefit of consumption. What is the increase to the group of giving it an additional unit when it's distributed optimally? But because everybody is identical, that unit gets distributed identical to everyone, so everybody gets 1/n of the extra unit. Okay? Now, what else do we know? We know that this is not the marginal social benefit. This is what is often called the marginal private benefit. The marginal social benefit is going to have to subtract this marginal damage. So it may be a subtraction, let's say like this. So that curve is going to be the marginal social benefit, and this gap at any point is going to be gamma n d prima of Q. Now, what do we find out? We find out from this graph that the optimal amount is with the marginal social cost is equal to the marginal social benefit, which is here. This is the optimal amount of Q. Now we can characterize the deadweight loss, which is the size of the inefficiency in this market graphically. We know that the market is going to produce at a point in which the inverse demand function, which remember measures the marginal private benefits, is equal to the marginal private cost, which is equal to the marginal social cost in this example, which is equal to mu. And that is going to give us this equilibrium of the market allocation. Now we also know that the marginal social benefit is going to be shifted left. And this marginal social benefit curve is going to be equal to the marginal private benefit minus gamma n d prime of Q. This is the marginal damage, the marginal externality that gets produced. So we know that the optimal amount is when these two curves intersect and is here. So this is the optimal amount. Now, of course, the question is, what is the deadweight loss? And the deadweight loss is going to be equal to this triangle. It's going to be the difference, the excess social cost over the marginal social benefits, which is going to be equal to this area. That's going to be the deadweight loss of excess production. Why am I calling this excess production? Because the key of the market is greater than the optimal. Now let's remember why this is a deadweight loss. This is the optimal amount. Every additional unit that gets produced has a marginal social cost of production that exceeds the marginal social benefit. Intuitively, why does the market produce it? Because when the individuals make their decisions, they only take into account the marginal private benefit, and that marginal private benefit exceeds the marginal private cost, which is the equilibrium price mu, all the way to the market equilibrium. But from a social point of view, this is the amount that we would have wanted to be produced, and this is the loss in total utility for the market that happens. I want to conclude this section of the video lectures with two remarks. First is we have looked at a very special model, a very simple model of public bats to derive some intuition in which all of the damage happens from consumers to consumers. But I want to emphasize that the finding that there is inefficient overproduction of a good Q when it induces negative externalities is a robust finding. You can extend the model in many other ways, as you will see in the problem says, and you will always have that Q star, the key of the market, is greater than the optimal amount. The second is that when you solve the problems, you're going to have to decide whether the externality is lowering the marginal social benefit or is increasing the marginal social cost. And in examples like the one I just gave you, this is a natural way of doing it, but in other examples it can get complicated. So I'm going to propose to you a normalization, a recipe, an accounting recipe for externalities, which is that damages or externalities that affect utility go into the marginal social benefit part, and externalities that affect cost or production go into the marginal social cost part. Let me emphasize, don't over worry about this, because as long as you're keeping your accounting correct, it doesn't really matter where you put it in terms of characterizing the optimal amount, the optimal policy, and all of that. But this, I have found over the years that this recipe really helps the students keep things clear. If you have an externality like pollution that is produced by consumers that affect the utility damage to consumers will go into the marginal social benefit part, whereas the part of the pollution that increases the cost of firms will go into the marginal social cost part. I hope that you find that recipe useful in solving problems.